Hello everybody! Today we are going to talk about bivariate linear regression. We will try to understand what that means and how we can use it. Take a look at the graph. We have the Cartesian coordinate system with x-axis and y-axis, and this scatter plot shows the dependence between x and y variables. We clearly see that these variables are dependent because this scatter plot is directed slightly upwards. So we can assume there is a linear positive relation of x and y. That would imply that with the increase of x, the y also increases. And we would like to model this stuff. We would like to construct a functional equation that would approximate the data and help us predict y given some known value of x. Basically, we are looking for the linear function with some parameters that would look like this. For example, y with the head sub I is equal to b0 plus b1 x sub I, where b0 and b1 are the parameters of this function. If we look at the parameters geometrically, b0 is the intersection of the regression line, this linear function, and y-axis, whereas b1 is the tangent of the angle between the regression line and the x-axis. Let's introduce the error term, and the error term, or the residuals, is the difference between the true value of the dependent variable y and the modeled value. It would look like this. You see, all these differences are our residuals, and we denote the residual E sub I be the difference between y sub I minus y with the head sub I, which is our modeled y. And this is also an equivalent to writing y sub I minus b0 minus b1 x sub I, since y with the head sub I is equal to this expression we touched before. So our goal in this case would be to find the values for these parameters. And we are doing that with the help of the statistics that we have. We can write that y sub I is equal to b0 plus b1 x sub I plus the residual term. And in order to fit the parameters to compute the values, we pick a special loss function that we will try to minimize. And the loss function will reflect our goal, which is to find the best fitting line. So we are seeking for the line that approximates data best. We don't need this line that goes like this because it is far away from the data. We need this one that is going as close to the data points as possible. That's why we would try to minimize the distances between the modeled y's and the actual values of y. If we take a look at the residuals, we can see that if the data points are above the regression line, then the residual would be positive. If, on contrary, the data point is below the regression line, the residual will be negative. And then we will find no solution if we keep it like this. So we take the squared residuals to try to find the best fitting line. And our loss function in this case will look like this. Don't be scared. It's nothing difficult. So Q of two arguments, B0 and B1, will be equal to the sum of squared residuals in order to get rid of the negative values of the errors which are lying below the regression line. So we are trying to minimize the sum of squared residuals. And if we replace E sub I in this equation with this expression, we would get just this form. Our goal is to minimize this target function by adjusting the parameters. This is very easy to solve. We just take the partial derivatives and set it equal to 0, and then we have the system of equations with two equations and two unknown variables. Since the function is parabolic, we have the square here. Then it has just one minimum, which we can easily find analytically. Since we are minimizing the sum of squared residuals, this method is called ordinary least squares, or OLS. Now let's take a look at two partial derivatives of this target function. You see, we take the first partial derivative on B0 and the second one on B1. It would look like this. You see, minus 2 sum, and in the parentheses we have y sub I minus B0 minus B1 x sub I. That's nothing difficult, it's just the partial derivative of this function on B0. And then the second one, the same for B1. Let's move on. That's what we ended up with on the previous slide. And let's just express from the first equation B0 via B1 and xi and y sub I. Let's remove the parentheses and simplify each of these equations. We would end up with the following form. You see, we just, by removing the parentheses and canceling minus 2, we have sum of y sub I minus sum of B0 minus B1 sum of x sub I equals 0. The same with the second equation. We remove the parentheses and cancel 2 and the minus, of course. And we end up with sum of x sub I y sub I minus B0 sum x sub I minus B1 sum x sub I squared also equals 0. Then take a look at this term, sum B0. What does it mean? It means it is B0 plus B0 plus B0 plus B0, and it goes on for n times. The n is the number of observations that we have. That's why we can replace this one with n B0. And then this expression will look like this. You see, we place this term into the right part of the equation. And now we have n B0 equals sum y sub I minus B1 sum x sub I. From this equation, it's very easy to express B0. It would look like this. And please note that sum of y sub I divided by n is y average, and sum of x sub I divided by n is x average, what gives us the expression of B0 through x average, y average, and B1. And then we just plug in B0 into this equation and get the following thing. Sum x sub I y sub I minus y average times sum x sub I plus B1x average sum x sub I minus B1 sum x sub I squared. Everything equals 0. If we simplify this expression a bit, we get the following thing. B1, and then in the parentheses we have the following expression. And these two terms we put in the right side of the equation. From this expression, it's very easy to get the analytical form for B1. It will look like this. And if we divide both numerator and denominator by n, we end up with even simpler form. That B1 equals xy average minus x average y average divided by x squared average minus x average squared, what can be also presented as the covariance of xi divided by the variance of x. And this is how we derive the analytical form for the coefficients of our regression line. I thank you for your attention, and I hope that you will continue watching my videos. Goodbye.